Hello everybody, and this is the first in a series of videos on motion, energy, and gravity. So we're going to start by talking about how we describe motion. And there's certain terms that you're already familiar with, but I want to make sure we're all on the same page with talking about what these words mean. So we have speed. That is the rate at which an object moves. It's how much ground it covers in a certain time. You also have velocity. Now, velocity is different from speed because it includes direction. So you might think of, a speed as being, I'm going to drive at 70 miles an hour, versus velocity, I'm going to drive at 70 miles an hour in an easterly direction. The direction part of it is important to velocity. Then we have acceleration. And acceleration is the rate of change of velocity. And so what we've got in this image here, we've got things that are accelerating. So here we've got a car that's moving from 30 kilometers per hour to 60 kilometers per hour. It is accelerating because its velocity is increasing. Now here we have a car that's moving at 60 kilometers an hour throughout, but it's changing direction. And so since its direction is changing, then its velocity is changing, and therefore it is accelerating. And finally, we have one here that's going from 60 kilometers an hour down to 0. That is also accelerating, but it's a negative acceleration. Sometimes we say decelerate. Acceleration is something that we're actually familiar with in our everyday lives because this is what gravity does. So here I've got a guy standing on top of a tall building, and he's got a ball, and he's going to drop that ball. And at time 0, the ball isn't moving at all. Once he drops it, a second later, it's going at 10 meters per second. A second later after that, it's going at 20 meters per second. How fast it gets to depends on how tall the building is. And this is because the acceleration due to gravity is 10 meters per second squared. So for every 1 second that the ball is falling, its velocity or speed is going to increase by 10 meters per second. Now, Galileo showed that this g, this acceleration that is due to gravity, is the same for all objects regardless of mass. So you can have something that is made of lead versus, made of feathers, and they're going to fall at the same rate as long as you don't have air resistance. So all falling objects accelerate at the same rate. And as I said, and you can see here, g, the acceleration due to gravity on Earth, is approximately 10 meters per second squared. So now we're going to look at what happens when we drop a ball from rest and what happens to its position, its velocity, and its acceleration as a function of time. So you can see it starts at 20 meters high, and over the course of 2 seconds, it is dropping down, it is changing in height. You can see that the rate at which it's changing is varying too. If you look at how its speed is changing, it starts at 0, it's not moving at the top, and over the course of 2 seconds, it is accelerating so that it goes up to 20 meters per second. At the same time, here we have acceleration, which shows that the acceleration is just 10 meters per second squared, and the negative sign here means that it's down. So positive is up and negative is down. If we now look at this from the point of view of a ball that starts at the ground, launches upwards and comes back down, we can see that it goes from the ground up to 20 meters high and then comes back down again. If we look at this from the point of view of its velocity, it starts off at 20 meters per second, but it's slowing down until it reaches its highest point, and at that point it has 0 velocity, it's not moving, and then it starts moving down, and so its velocity becomes negative. But all the time, the acceleration, that is how much the velocity is changing, stays constant. So let's now talk about momentum and force. Momentum is just mass times velocity. And here you can see a cartoon of Newton's cradle. Here I've got masses that are on the ends of strings, and the end ones are moving side to side. So here you can see this far left-hand ball. When it's moving, it has a momentum that is its velocity times its mass. Each of these balls has a mass. They're all identical. But if they're not moving, they have 0 momentum. Now, if you want to change momentum, you need a force. So here we've got this left-hand ball again, and it is moving. Some of the time it's moving to the left and some of the time it's moving to the right. So there must be a force acting on it because its velocity is constantly changing, and it's changing because there is the force of gravity onto it. Usually it's an acceleration that is involved if you are changing momentum, because things don't usually change mass very much. There's also a thing that is a rotational version of momentum. This is if you have a spinning or orbiting object, that momentum is called angular momentum, and we're going to get into a little bit more on that shortly. So let's consider things that are moving in circles. Angular momentum is going to describe objects that are spinning or moving in circles. So if you imagine that you've got a ball on the end of a string and you're spinning it round in circles, it's got a certain amount of angular momentum. How much angular momentum it has depends on how fast it's moving, how massive the ball is on the end, and how long the string is. If you want to change the momentum of something that has angular momentum, if you want to change the angular momentum, you have to apply a special twisting force called a torque. So just like you need a force to change the momentum of an object moving in a straight line, you need torque, which is a twisting force, to change angular momentum. So if we think about what's going on with the Earth orbiting the Sun, here I've got the Sun in the middle, the Earth going around in its orbit and spinning on its axis. So it has angular momentum related to its rotation and angular momentum related to its orbit. Both of those are circular motions. So let's shift gears now and talk about why mass is different from weight. So mass is a measure of how much stuff there is in an object. So my mass is how much stuff am I made of? Weight, on the other hand, is the amount of force that a scale exerts upon an object. So if I'm standing on a regular weighing scale, it is the force of gravity that's pulling me down. Gravity is pulling me down, and I'm exerting a force, and it's related to my mass, but it's not the same thing. And so if you're on Earth and you weigh 100 pounds and you go to the moon, then on a weighing scale, you're only going to weigh 16.6 pounds because the gravity is lower, and so the force that you exert on that weighing scale is less, even though you still are the same amount of atoms, the same amount of stuff that you're made of. So let's consider this idea for a minute. Here I have a guy in an elevator, and the elevator is either moving just at a constant velocity, so it's the same speed all the time, or it's just stationary. And in that case, if you were standing on the weighing scale, your weight should be normal. 140 pounds seems light to me, but not better. If you are moving upwards, though, then that upward acceleration is adding to the weight that you have. And so now the weighing scale will register a higher number. You will have a higher weight. Even though your mass hasn't changed, your weight will be more because the elevator is accelerating upwards. If the elevator is accelerating downwards, you weigh less. Now you're counteracting gravity, and you're going to not put as much force onto the weighing scale, and so you weigh less. If the cable snaps and you are free falling, you are now weightless. We'll come back to this idea in future videos. This is basically why astronauts float free. It's not because there's no gravity in space, it's because they are free falling. So you are weightless in free fall. And that's all for this first video on motion and energy.